Pluto is a far-off and puzzling planet. Pluto was once an individual member of our nearby planet social gatherings and planetary family. However, recent revelations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They propose that this cold world is on a potential collision course with Neptune. But how could this happen, and what might be the outcomes of such a catastrophic event? Are we witnessing a significant cosmic anomaly, or is there something more to this approaching cosmic catastrophe? Join us as we examine the potential consequences of a Pluto-Neptune collision. Pluto, a former planet that was demoted to a dwarf planet primarily due to its erratic orbit, remains a subject of interest and study in the astronomical community. Recent estimates by leading researchers show that Pluto's orbit is dangerously close to Neptune's. Tyson and Kaku are both raising alarms about a potentially hazardous crash between these two planets, which could represent a significant risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike any other planet in our nearby planetary system. It takes an astounding 248 years to complete a single orbit, and since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue surrounding Pluto doesn't stop there. Pluto's orbit is marked by its exceptionally curved shape, deviating significantly from the almost round orbits of the major planets. What makes Pluto's orbit even more bizarre is its inclination, shifted at 17 degrees to the ecliptic plane. The way Pluto follows its path is much steeper compared to the other planets, adding a layer of complexity to its orbital movement. One of the most intriguing aspects of Pluto's orbit is its interaction with Neptune. For nearly 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying our expectations based on their positions in the solar system. This leads to the common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began soon after its discovery, as astronomers tried to figure out its unusual path. Unlike other planets whose orbits lie fairly close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened when it was realized that Pluto's orbit indeed crosses Neptune's. Despite these complications, the stability of Pluto's orbit amid these intricacies is evidence of the complexity of celestial mechanics. The three-body problem in space involves determining how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other through their gravity. It's akin to predicting where these bodies will go based on their starting points and how they pull on one another. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex manner. Key terms such as Amal libration, degree libration, and the VZK oscillation are essential to understanding this enigma. According to astrophysicists, what keeps planets in their orbits is the concept of libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned roughly 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Degree libration refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned well above their orbital plane, providing an additional layer of protection against potential collisions. Another important element is the VZK oscillation, named after three scientists, Bond, Zippel, and F, who studied how objects move in space. It refers to how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This gravitational pull influences their movement. For Pluto, the VZK oscillation helps us understand why its orbit around the Sun is so unique. Despite Pluto's orbit appearing chaotic, this oscillation helps maintain its smooth movement for extended periods. These factors help keep Pluto's orbit stable, ensuring it doesn't crash into Neptune or veer off course. The three-body problem helps us understand how these forces change based on how these space objects pull on each other. Studying this phenomenon helps us learn more about Pluto, our solar system, and distant worlds. Mathematical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is indeed turbulent. Slight deviations in initial conditions can lead to enormous differences over centuries. However, these exceptional properties of Pluto's orbit have been found to maintain stability over extremely long timescales, effectively preventing chaos. Later computer simulations helped us understand how giant planets like Neptune, Jupiter, and Saturn impact Pluto's path around the Sun. Neptune has a special relationship with Pluto in which, for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's orbit predictable. However, Neptune isn't alone. Jupiter's gravity also plays a crucial role in stabilizing Pluto's orbit. In fact, Jupiter's gravity alone is enough to ensure Pluto remains on a steady path for many years, even billions of years. It seems that Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely through space without running into trouble. These idiosyncrasies are crucial in the broader context of the universe, maintaining control and consistency in celestial body movements. Without these factors, our nearby planetary system would be much wilder and more turbulent. Bodies like Pluto could collide with others or be ejected from their stable orbits, leading to impacts on other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is essential. It provides a clearer picture of the dynamic nature of the solar system. The case of Pluto demonstrates how even the most seemingly unstable orbits can achieve balance through the complex interplay of gravitational forces and orbital mechanics. It also underscores the importance of constant observation and analysis of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the whimsical nature of celestial bodies, and Pluto's orbit is an ideal representation of this whimsy. The concept of orbital tumult, which refers to the delicate dependence of a celestial body's path on its initial conditions, is strikingly illustrated in the case of Pluto. Even slight variations in Pluto's position or speed can dramatically alter its long-term orbit. Using computer simulations has been incredibly helpful for scientists to figure out how Pluto moves in space. These simulations use advanced mathematics to show how Pluto and other space objects, like Neptune, pull on each other. By adjusting small details in the simulations, astronomers can see how even minor changes can make a huge difference in where Pluto ends up. In the late 1980s, these simulations revealed something very interesting about Pluto's orbit. Despite factors like Amal and degree libration stabilizing its path, Pluto's orbit can still be chaotic and eccentric. Starting with just a small difference in Pluto's position or speed can cause its orbit to look very different over many years. However, despite this chaos, Pluto's orbit remains stable for extended periods, like billions of years. This means Pluto's journey around the Sun has some order to it, even though it may seem chaotic at first. Predicting future events, especially involving unstable orbits like Pluto's, presents significant challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a solid means to understand and predict the future behavior of celestial bodies, they also highlight the limitations of our forecasting abilities. These models rely heavily on the accuracy of initial conditions, and any slight error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we've made great strides in understanding space, the case of Pluto serves as a reminder that our knowledge of the universe is still limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the position of each planet can significantly influence the stability and trajectory of other bodies within the system. The future of Pluto and Neptune's orbit. So why are prominent astrophysicists only now raising concerns about a possible crash between Pluto and Neptune, despite all these complex forces working to prevent such an event? Neil deGrasse Tyson, a well-known astrophysicist and a key figure in advocating for cosmology, offers a unique perspective on the mysteries of our solar system, especially the captivating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the dark realms of space. Tyson's stance on Pluto's renaming is rooted in our growing knowledge of the solar system. He views the renaming not as a demotion but as an important shift in our understanding of the various bodies orbiting our sun. His approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a sign of how much more there is to discover in space. The interest in these questions, particularly the potential interactions between Pluto and Neptune, highlights the dynamic and often unpredictable nature of our solar system. His work emphasizes that the more we uncover about space, the more questions arise, driving us to explore further and refine our understanding of the universe. Michio Kaku, another eminent physicist and futurist, offers a different yet complementary perspective on the mysteries of space, focusing on the often whimsical forces that shape our universe. Kaku is known for his ability to connect complex scientific ideas with cutting-edge visions, making him a significant voice in discussions about celestial mechanics and the broader implications for humanity. Kaku's insight into the future of space exploration suggests that new technology, including advancements in artificial intelligence, will soon allow us to peer deeper into the cosmos than ever before. With this ability to observe space more effectively, he suggests we might soon gain answers to questions like whether Pluto will ever crash into Neptune or how future interactions between cosmic bodies might evolve. Conclusion: the final frontier. As the debate around Pluto's orbit and its potential collision with Neptune continues, we are reminded of the incredible complexity of the cosmos. From Pluto's bizarre orbit to the innovative simulations that help us understand its motion, our understanding of space is constantly evolving. It's a reminder that the universe is filled with surprises and mysteries, and there's always more to learn about the vast reaches of the cosmos. With scientists like Tyson and Kaku at the forefront of this exploration, we continue to expand our knowledge of space and the forces that govern it. Ultimately, the potential collision between Pluto and Neptune, however unlikely, represents the unpredictable beauty and complexity of the universe that we can only begin to understand. *** Pluto's cosmic evolution. A deeper look at its orbit ***. As scientists continue to explore Pluto's orbit and its interactions with Neptune, a more nuanced understanding of celestial mechanics begins to emerge. The complex dynamics of Pluto's path around the Sun reflect the intricate relationships between various planetary bodies in our solar system. Pluto's journey has been anything but ordinary. For a long time, its status as a planet was unquestioned, but as our understanding of the solar system evolved, so too did our classification of Pluto. The concept of a planet has expanded to encompass a wide variety of celestial objects, many of which are found in the outer reaches of our solar system. In recent years, the discovery of many other small icy objects in the Kuiper Belt has reshaped our understanding of what constitutes a planet. The debate surrounding Pluto's reclassification highlighted the need for a clear definition, and the introduction of the term dwarf planet allowed astronomers to classify Pluto in a way that acknowledges its unique characteristics. However, this shift was not universally accepted, and Pluto continues to capture the public's imagination as a once prominent member of the planetary family. This shift in Pluto's classification has also reignited interest in its interactions with other planets. While the idea of a collision with Neptune might seem far-fetched given their complex orbital relationship, it also prompts us to consider the larger forces at play in the solar system. One of the key aspects of understanding Pluto's orbit is the role of the Sun's gravitational influence. The Sun remains the dominant force in the solar system, dictating the movement of planets and dwarf planets alike. However, the interactions between planetary bodies like Pluto and Neptune are also influenced by the gravitational pulls of other objects in the solar system, such as Jupiter and Saturn, which add an additional layer of complexity to the overall dynamics. These interactions are far from static. Over millions of years, gravitational forces from larger planets can shift the orbits of smaller objects like Pluto, which leads to the potential for orbital resonances. This is why Neptune and Pluto, despite their seemingly unstable orbits, can coexist without colliding. Gravitational resonances help maintain the stability of their orbits by forcing them to follow specific, predictable patterns. These resonances create a delicate balance that has allowed Pluto to maintain its place in the solar system for billions of years. However, Scientists are constantly refining their models of these interactions, using advanced computational techniques to simulate the future behavior of these distant objects. These simulations not only predict the potential for a collision between Pluto and Neptune, but also help astronomers understand the long-term stability of other bodies in the Kuiper Belt. Understanding Pluto's orbital behavior is essential for predicting the evolution of the solar system as a whole. The work of researchers like Tyson and Kaku highlights the importance of continued observation and refinement of our understanding of space. As technology advances and our ability to observe distant regions of the solar system improves, we may uncover even more mysteries about Pluto and the forces that govern its movement. In the end, the unpredictable nature of celestial mechanics reminds us that space is filled with both beauty and chaos, and our exploration of it is far from over. The journey of understanding Pluto and its relationship with Neptune is just one example of how much more there is to discover about the universe and the forces that shape it.